Welcome. Today, we are diving deep into an invisible force that, honestly, shapes our entire world. It's the reason atoms stick together to form molecules. It's why lightning rips across the sky, and it's even why the very device you're watching this on works at all. We're talking about Coulomb's law, and trust me, it's one of the most fundamental rules in all of physics. You know that tiny little spark you feel sometimes when you touch a doorknob? Or maybe you've rubbed a balloon on your head and watched it just magically stick to the wall? Well, that's not magic, it's physics. And the rule behind all of it is exactly what we're going to break down today. So here's our game plan. We'll start with what the law even is, then figure out how to calculate the force's strength. After that, we'll add direction into the mix with vectors, put the electric force head-to-head with gravity, walk through a really cool example, and then wrap it all up with the key formulas you need to know. All right, so first things first. What exactly is Coulomb's law? Well, at its core, it's the fundamental rulebook for how charged things push and pull on each other. But before we can really use it, we have to understand a really important simplification that makes all the math possible. And that simplification is this idea of a point charge. Just imagine two charged objects, let's say two little spheres, that are really, really far apart. From that distance, their actual size and shape don't really matter anymore. They act as if all their charge is squished down into a single, tiny point. Now, this is a fantastic trick because it lets us ignore a bunch of messy details and focus on the only two things that really matter: how much charge there is and how far apart those charges are. So here's the bottom line. Coulomb's law gives us the exact numbers. It's not just about saying, oh, they push each other away or they pull together. It tells us precisely how hard they're pushing or pulling. It turns a general idea into a hard, quantitative law we can actually use. Okay, so let's get right into the heart of the law. We're going to start with the simplest version, the one that just tells us the raw strength or magnitude of this invisible force. And here it is. The force, which we call F, is equal to a special constant, K, multiplied by the two charges, Q1 and Q2, and then divided by the square of the distance between them, R. And notice those absolute value bars around the charges? That's because right now we only care about the strength, not whether it's a push or a pull. We'll get to that in a minute. This table breaks it all down for us. Force is measured in newtons, distance in meters, and charge gets its own special unit, the Coulomb. And that letter K is what we call Coulomb's constant. It's just a number that makes the units work out, but look how big it is. It's about 9 billion. That huge number is our first clue about just how incredibly powerful this force really is. To really give you a feel for this, check this out. 1 Coulomb is a massive amount of charge. If you could somehow place two objects with 1 Coulomb of charge each, just a meter apart, they would blast each other away with a force of 9 billion newtons. That's like the weight of more than 1,500 jumbo jets. So in the real world, we're almost always dealing with teeny, tiny fractions of a Coulomb. Okay, so now we know how to find the strength of the force. But that's only half the story, isn't it? Is it a push or is it a pull? To answer that, we need to bring in the idea of direction. This is probably the one rule you remember from science class. Like charges repel and opposite charges attract, right? Two positive charges push each other apart, two negative charges do the same, but a positive and a negative will always pull towards each other. So the big question is, how do we build this simple rule into our formula? This is how physicists do it. They use vectors, which are just arrows that show both direction and size. So we start by setting up a map, an origin point. The vector R1 is an arrow pointing from our origin to the first charge, Q1. And the vector R2 points from the origin to the second charge, Q2. But the most important arrow here is R21. That's the vector that points directly from charge 1 to charge 2. It perfectly captures the line between them. Okay, now here is the really clever part, how the math handles attraction and repulsion. First, that symbol F21 means the force on charge 2 caused by charge 1. To get the direction right, we use something called a unit vector, which looks like R hat 21. Think of it as a pure directional arrow. Its length is always exactly 1, so it doesn't mess with the strength of the force. Its only job is to point from charge 1 towards charge 2. Now watch this. If the charges are the same, like two positives, their product Q1, Q2 is positive. The force points in the same direction as our arrow. It pushes charge 2 away. They repel. But if the charges are opposite, their product is negative. That negative sign literally flips the direction of the force, making it point opposite our arrow, pulling charge 2 back towards charge 1. They attract. It's just a beautiful, elegant way to build a physical rule right into the math. So here it is, the full, complete vector version of Coulomb's law. I know it might look a little intimidating, but we've actually gone through all the pieces. You might notice that K has been replaced by this 1 over 4 pi epsilon naught thing. Don't let that throw you, it's the exact same number, it's just written this way because that little symbol, epsilon naught, is a more fundamental constant of the universe that pops up in other important equations. The rest of it does exactly what we just talked about. It calculates the strength and then uses that clever little unit vector to point the force in the exact right direction. Now that we've got a handle on this force, let's get some perspective. Just how strong is it, really? And the best way to do that is to put it in the ring with the force we're all familiar with, gravity. Just look at how similar these two laws are. It's kind of wild. Both depend on a product of two properties, mass for gravity, charge for electricity. And both forces get weaker with the square of the distance. But there is one absolutely profound difference right there in the table. Gravity only ever pulls. It is always attractive. The electric force, on the other hand, can both push and pull. So let's actually run the numbers. Let's take a single proton and a single electron, the building blocks of a hydrogen atom. They have mass, so they pull on each other with gravity. And they have charge, so they pull on each other with the electric force. Which one do you think is stronger? Well, it's not even a fair fight. The electric force is stronger by a factor of 2.4 times 10 to the 39th power. Let that sink in. That's not 39 times stronger. That is a 2 with 39 zeros after it. On the scale of an atom, the electric force is so completely dominant that gravity is basically a rounding error. It just doesn't matter at that level. Okay, theory is awesome, but let's see how this all plays out in a real problem. This is a classic example that really ties all these ideas together. So here's the setup. We start with two charged spheres, A and B, that are 10 centimeters apart, and they're pushing on each other. Then we bring in two identical but uncharged spheres and touch one to A and one to B. This lets the charge spread out, so it cuts the charge on A and B in half. Then we take those extra spheres away and move A and B closer together to just 5 centimeters apart. The question is, what's the new force? Let's think this through. First, we cut each charge in half. Since the force depends on Q1 times Q2, the new force becomes half times half, or 1/4 of what it was. Okay, so it's weaker. But then we cut the distance in half, and the law says the force goes as 1 over the distance squared. So having the distance doesn't double the force. It makes it 4 times stronger. So we have one thing making the force 4 times weaker, and another thing making it 4 times stronger. And in this case, the two changes cancel each other out perfectly. Incredibly, the final force is exactly the same as the force we started with. Wow, okay, we have covered a lot of ground, so let's take a second and lock in the most important points from all this. So, here are your key takeaways. You've got the scalar form for just calculating strength, and the more complete vector form for getting both strength and direction. The core principle, never forget, likes repel, opposites attract. And finally, that key insight. At the scale of atoms and molecules, the electrostatic force isn't just the main character, it's pretty much the only one on stage. You know, Coulomb's law is absolutely perfect for figuring out the force between 2 point charges. But what happens when you have 3 charges, or 4, or trillions upon trillions of them, all pushing and pulling on each other at the exact same time? How could we possibly describe that incredibly complex web of forces? Well, that question leads us directly to our next huge idea in physics, the electric field.